Hello everyone. Today we'll be explaining the concept of energy harvesting using vibrating beams, and we've made a model over here to demonstrate the same. Okay, so I'll be explaining the various parts of this model. So we have used a wooden frame. We have used a wooden frame, and we have a beam which is 4 mm thick stainless steel, and we have magnets mounted on the beam at one end, and the beam is a cantilever beam. It is supported at one end by a rigid support, a fixed support. You have to, these are the coils. These two are induction coils, and they are bolted onto the frame using these blocks, these wooden blocks, and there are slots on the sides for sliding the coils fore and aft, as I'm showing with my hands. And you can vary the effective length of the vibrating beam by loosening these nuts and shifting the entire beam forward or backward. As we couldn't use this on an actual machine to demonstrate energy harvesting, we decided to give it an excitation of our own by using a motor. And this circuit over here is used for speed control of the motor. If you look at the theory of vibration energy harvesting, you'll find that maximum energy is produced at resonance. That is when the beam is vibrating at its first mode, and the excitation frequency matches the resonance frequency of the beam. That is, we are using the first mode vibration over here, first mode excitation over here, where the maximum amplitude of motion will occur at the tip of the beam. You have these magnets here, as you can see, and the beam is cantilever, and that is the stiffness. So the magnets move in and out of the coil, and due to electromagnetic induction, you can see these two coils have been put in series, and the outputs can be found at these 2 points. So yeah, these two are the points where you can find the output of the beam, output of the coils. The output will be a few millivolts because the exciter that we have used, and the imbalance, this is an imbalance for the excitation, and the motor is quite small, as well as we couldn't exactly tune it to natural frequency. This circuit over here controls the speed of the motor, the RPM of the motor, and if we vary the RPM of the motor from a particular value in a particular range, and we found that for a particular frequency it vibrates with maximum amplitude over here. So now we will demonstrate the functioning of this, and I'm going to connect the battery in and let the motor start, and then I'll be tuning it to the natural frequency, and you'll be able to see the voltage generated on the screen over here. But do note that the coils in series, they will be producing an AC voltage, and which is why you'll see the sign keeps changing in the voltage over here, and that this is a digital multimeter, and it won't be able to capture the small variations in voltage, the small rapid variations in voltage that is proportional to the frequency over there, and hence the voltage will be fluctuating between a few values with a peak value being shown. Okay, so I'm going to connect the battery in. So there I go. Yeah, so if I tune the motor to the correct voltage, you can see that peak voltage of around 2.5 millivolts, and the sign keeps changing, so that shows the potential changing sign. So yeah, that's the demonstration of this using the motor as an excitation. Next, we'll be showing the demonstration by using free vibration. So now we'll be demonstrating free vibration on the same setup, and this is supposed to function as a forced vibration setup, and the tuning of this setup for various natural frequencies of the machine that for various input frequencies, excitation frequencies, for whichever application. So let's say you have a motor housing that is vibrating at, let's say, 500 Hertz. So this beam's natural frequency can be tuned to match that particular housing's natural frequency, and this entire setup can be mounted on that. The tuning can be done in a particular for a given range of frequencies by varying the length of the beam as well as moving the coils along, okay, and moving the position of the magnet on the beam. So right now I'm going to demonstrate how there is a this multimeter is set to millivolts, and I'm going to demonstrate how voltage is generated when I give the excitation using my hands. So as you can see, there is a it goes up to 20 to 30 millivolts. If you have a constant source onto which you can mount the setup, and if the natural frequency matches this setups, then you can generate quite a bit of potential from it. And there are various applications for this. If you are able to miniaturize this, you'll be able to use it in maybe running some sensors or some diagnostic equipment. It won't be able to give you much power, but a few sensors or data acquisition can be performed using the energy generated by this. So thank you.